So far, what methods have we learned? We learned some methods for doing regression, and this was mostly linear regression, and this was the topics that was already in the textbook. But regression is not the end of the world, because our output variable could be a categorical variable. And if the output variable is categorical, then our task is going to be different from regression. It's going to be classification. And we learned a bunch of techniques for classification. We started with k-nearest neighbor, then we learned about multinomial logistic regression, then we learned about naive Bayes. These are all for classification. Uh, then we learned about neural networks. We learned about support vector machines. We learned about decision trees. We learned about random forests, and we learned about AdaBoost. So these are for classification, and all of the examples that I just listed, you had input, output data. You have pairs of input and output data. The input data was your features. The output data was your labels. It was either continuous or categorical. It was either a regression framework or a classification framework. Whenever you have pairs of input, output data, your problem, your machine learning problem, is a supervised problem. And the supervision is coming from labels. Whenever your data doesn't have any labels, because labeling is an expensive task. Somebody needs to write down and collect data and label your data. For instance, in image classification, somebody needs to look at your images and say, there is a cat in this image, there is a dog, there is an airplane, etc. So somebody needs to label. And that's supervision. A human is supervising your machine learning framework. So the task of labeling is the task of supervision. If you don't have labels, that's going to be an unsupervised technique. That's going to be unsupervised. So machine learning, you can divide it into two big fields, supervised and unsupervised. Now we're going to move towards unsupervised. And the question is, can you, if I give you the input data only, and if I don't give you the labels, can you automatically label them for me? Can you categorize? Can you put all of the categories that are similar to each other, all of the data that are similar to each other in one category, and put the other ones in another category? And a famous algorithm for that is k-means. It's a very simple algorithm, but it's extremely powerful. So what are the problems that we need to solve? First of all, somebody needs to tell us how many categories do we have. And when it comes to clustering, the category is going to be called clusters. How many clusters do we have? Let's say this is your data, and you want to cluster it into two categories. So how k-means is going to approach that problem is going to say, I'm going to start with 2 points in my space at random. So these are 2 random locations. This is called the centroid. This is called another centroid. So you have 2 centroids, the red centroid, the blue centroid, and your algorithm is initialized randomly. So these points are randomly initialized. You just put them in your space at random. These are your centroids. The next step of k-means is to put all of the data that are closer to this red cross in the cluster of reds, and put all of the points that are closer to the blue cross in the cluster of blue. Okay, so you look at this data point, you measure the distance to this cross, the red cross, you measure the distance to the blue cross. This is closer, this is smaller than this distance, so you're gonna color that as red. You do that for every single one of your data points. So this data point is closer to blue, so you're gonna color it blue. Perfect. In the next iteration, what you're gonna do is compute the mean. That's where the mean is gonna come in. You're gonna compute the mean of these blue data points. That's gonna give you a mean x coordinate, a mean y coordinate, and that's how you update your cross, the blue cross. You do the same thing. You compute the mean of the red cluster. That's gonna give you an x coordinate. It's gonna give you a y coordinate, and that's gonna give you another cross. So that's how you update your crosses. Initially it was random. Now your data is speaking. Perfect. Now you're gonna look at your data points again. You look at this data point, it is closer to the blue, so you're gonna associate it to this cluster. This data point is closer to the red, so you're gonna associate it to the red cluster. Now you have two clusters, your clusters are updated. Then you're gonna go ahead and compute the mean of the blue cluster. It's gonna update X. You're gonna compute the mean of the red cluster, and it's gonna give you the updated X. So that's why it's called k-means. K is the number of clusters you have. In this case, it's 2. Means because to update the centroids, you are taking multiple means per each iteration. So that's how k-means algorithm works, and it's exactly how it is implemented in practice. But in the end, the objective function, all of the machine learning, actually most of them, are just an optimization scheme. You have your data, you have your means, you have your clusters, and then the objective function is you want your data points to be closer to your means, and then the loss function that you're using is just the square error of these two, the square distance. Is everything clear? The difference between clustering and classification is that for clustering, you don't have any colors for your data. You don't know the labels. Your algorithm has to come up with the labels on its own. And then these points are one cluster, these points are going to be a second cluster, and then you color code them accordingly. Is this clear? So are the centroids initially placed in a random location? Then they are updated? Yes, exactly. So initially, these are randomly located in your space. And there is also another technique that people use, that's k-means plus plus. That's when you have multiple starts. So you have multiple random initial locations for these two points. But that's more advanced topics. For now, that's the general picture. Does that answer your question? Yes, initially they are random. Any other questions? So is this clear? Perfect. Now we can move on. What library are we going to use? It's library cluster. This is just for visualization purposes. Then we are going to do a k-means on our iris data. But look at this. Let's take a look at iris. Iris has 5 columns, 1, 2, 3, 4, 5. But then we are going to use only the first 4 columns. So we are throwing away the labels. We don't need them for k-means. That's exactly what I did here. The first 4 columns. How many centers are we going to look for? We're going to look for 3 centers. Now, a great question here is, why are you choosing 3? Why not 4? Why not 2? And the way to answer such questions is using your validation data. You look at your validation data, you define a performance metric for clustering, and using that performance metric, you're gonna choose the one that is giving you the best result on your validation data. Okay, that's the role of dividing your data into training, validation, and testing. And as I said, these random uh, initial locations, you can have multiple restarts and choose the best one in the end. So for number of restarts, we are going to use 25. And then we can take a look at the model. Then we asked for 3 clusters. The cluster means are the centroids. This is the first centroid, this is the second centroid, and this is the third centroid. What this vector is telling us is that this data point should be in the second cluster. This data point should be in the second cluster. This data point should be in the third cluster. This data point here should be in the first cluster. So that's how you interpret these results. And these are some performance metrics that you can actually use for comparing whether I should use 2 clusters versus 1 versus 3, etc. These are your performance metrics. And there are some variables here. If you want to look at the clusters, you can say model, and then you can say clusters or cluster. Then it's going to give you the clusters. So you can choose the clusters or any other variables that you like. And you can go ahead and visualize. This is a nice visualization package for clustering. So we had 3 clusters, and you can see that our data is being clustered nicely. So there is a cluster here for the iris data, there is another cluster here, and there is another cluster here. So it's a good technique for visualizing your data as well. And then this is just to make sure that our algorithm is doing something useful For this data, for the iris data, we threw away the last column. We threw away the fifth column, which was our labels. Now to test whether our clustering is doing something meaningful, we can include the fifth and just use that for color coding. We can use the labels to color code. And let's plot sepal length versus petal length. The clusters, we are now color coding them with the underlying labels. So actually the color is coming from the clusters, cluster 1, 2, 3, and the label, these letters that you see, they are coming from the true label. And you can see that actually the clustering is doing a very good job clustering our data without even knowing the labels. So it's putting all of the setosas in one cluster. It's putting most of the versicolors in one cluster, and it's making some mistakes. For instance, Virginica is in cluster 3, but it's okay. It's making some mistakes. It's putting some Virginicas in the cluster of versicolor, but it managed to separate out setosas entirely for us. And then in Virginicas, there might be some versicolor. I cannot see, but maybe this is a versicolor. Yes. So it's also making some mistakes there. But overall, without giving it the underlying truth, without giving it the labels, it managed to come up with 3 clusters. And it's separating our labels, our data in a nice way. And here I'm just using the Ggplot, so it's nothing complicated. And we learned about Ggplot a lot. And then the other one that I'm using is geomText that probably we haven't used, but it's a very nice way to visualize our data. Any questions so far?